graphs of the time path. Okay, I'm gonna do the graph of the time path in RStudio, but you can also find them in on the subject. Okay, so I'm generating a vector of 10 elements here, and look, now I'm just simply producing producing values of the complementary function for different values of b. So this will be the same values we discussed during the lecture. So it's 2, 1, 0.5, 0, negative 0.5, negative 1, and negative 2. And I'm filling them with values. So now just t takes values from 0, from 1 to 10. Okay, and let's look at the plots. Okay, and now we can zoom in. Look, what is important in this case is to remember that in case of difference equations, the graphs are not going to be solid lines. It makes perfect sense. Of course, these are difference equations. So we've got period analysis. They only take values at certain points in time, denoted by integers. So look, now let's go step by step through all the possible cases we had there. So first, we had the case where b is equal to 2. And look, what do we see? At the beginning, in the first period, b's deviation from equilibrium is 2, then it's 4, then it's 8, 16, 32, is 64, 128, 100, 256, 512, 1000 to 1024. So, and look, even though, look at the scales. On vertical axis, we see it goes up to 1000. We see that with b equal to 2, even though at the beginning we are very close to equilibrium, we are moving further and further and further away from it. And even in 10 periods, we are over 1000 units away from equilibrium. So definitely, in this case, we see divergence of the time path from the equilibrium value. Equilibrium value, of course, here is assumed to be 0 for simplicity, and it's assumed constant. It's denoted by this red horizontal line. So here we have an example of dynamically unstable equilibrium, and we have divergence. Look, in the second case, we have b equal to 1, and look, over here we see that it doesn't really matter to which power we're going to take b, we're always going to get 1. So look, this is a situation where in period 1, variable is thrown out of the equilibrium 1 unit away from it, and it stays 1 unit away. But remember, in this case, we are simply assuming that a, so arbitrary constant, is equal to 1. If arbitrary constant is the initial shock to the system or to the variable, if a in this case would be 7, we would be somewhere above here, and we would continue to be above. And look, what is important, if a would turn out to be, for example, negative 2, we would start at negative 2, and we would continue to maintain at negative 2, so 2 units below the equilibrium. And remember, in this case, for simplicity, we are assuming that equilibrium is equal to 0. And look, but this is the feature that appears in all the possible cases, because look here, if we would start at, if a would be negative 1, we would have approximately the same outcomes. We would have exactly the same outcomes as you can see here, but they would go below the equilibrium. They would be moving further and further away. Okay, and finally, so in this case, we have unstable equilibrium, but we do not have either divergence or convergence. We call this case non-convergent, but we see that once we are out of the equilibrium, we stay out of this equilibrium. This is the situation that is associated with the unit root that we are going to discuss later, and that you probably heard about during your econometrics class. Okay, so now let's move to the case of b equal to 0.2, and look, here we see that that we start at 0.5, and now with each consecutive time period at 0.5, so 1 over 2 is taken to a bigger and bigger power, the value of this expression shrinks, and we're getting closer and closer to equilibrium. And look, basically after 10 periods, we are at equilibrium. We are at 1 over 1024. Okay, the case number 4 was with b equal to 0. Of course, I'm sorry, this case, of course, described convergence and stable equilibrium. Now with b equal to 0, we again do not observe any convergence or divergence. Here, 0 taken to any power 1, 2, 3, 4, 5, 6, 7, still 0. But this is dynamically stable situation because we are maintaining in equilibrium all the time. Okay, and now there are only 3 more cases left. So let me just put them on the graph. Okay, so now if b is equal to negative 0.5, of course, as t gets bigger, absolute value of b gets smaller and smaller and smaller. As you see here, we have convergence. But look, unlike in the previous cases, we have here negative value of b, and what does it do? Look, we start at negative 0.5, we move to 0.25, then we have negative 0.125, then 1 over 16, negative 1 over 32, 1 over 64, negative 100, 1 over 112, and 28. And look, here again we definitely observe convergence. As t progresses, we are getting closer and closer to equilibrium, but this time we see the oscillation around equilibrium. This is a feature that we didn't have in differential equation, but it's very common in difference equations. And oscillations are produced, of course, by negative b's that make the values of the function fluctuate around equilibrium. Okay, and now, so what happens when b is equal to negative 1? Again, this is a case where we do not have either convergence or divergence, so we have non-divergence or non-convergence, but we have definitely dynamic instability. Why is that so? Because look, here, once the system is thrown out of the equilibrium, we see these uniform fluctuations because we move from negative 1, 1, negative 1, 1, negative 1, 1, and so forth. The system never goes back to equilibrium. And remember, what is important in all of these cases, here we assume that arbitrary constant is 1. If arbitrary constant here would be negative 2, we would start at 2, we would have negative 2, 2, negative 2, 2, negative 2, and so forth. And finally, the last possible case is with negative b bigger than 1 in terms of absolute value. In this case, we have b equal to negative 2. And look, what is happening over here? Again, we are fluctuating around equilibrium, one's going below, one's above, below, above. But in this case, as t progresses, absolute value of b is becoming bigger and bigger, and we see further and we see exploding oscillation around equilibrium. Like here, I think it's okay. So it's 2, -2, 4, -8, 16, -32, 64, -28, 256, -512, and 1024. So you see, with each consecutive period, we are moving further and further away from equilibrium, but we are moving in both directions because we have oscillation. Okay, and I think this is it. In the next movie, we will learn a little bit more about association between econometrics and first order difference equations. Thank you for your attention.